Hello, welcome. Today we're going to be doing some limit notation and how to compute very basic limits in calculus. We will not be going over any proofs for limits. That might be in a later video. So let's start off with the basic notation. A limit can be expressed as in the following way. A limit as x approaches some number x naught of f of x is equal to L. You say this as the limit as x approaches x naught of f of x is equal to L. An example is this following limit. So how would you say this? The limit as x approaches 2 of x squared is equal to 4. How about this one? The limit as x approaches negative 5 or minus 5 of x cubed is equal to minus 125. This is very important as we want others to be able to understand what we're saying when we're talking about math. Now that we got that out of the way, what does the limit even mean? So let's look at the following graph. Let's observe f of x around x equals 4. A limit is a method of approaching what y value corresponds to a certain x value from both sides. In this case, if I wanted to find the limit as x approaches 4 of this f of x here, we have to look at what happens as we follow the graph toward that point, but not quite at the point, from both sides actually. A better way of thinking of this might be the following. Here we have two rectangles, kind of. So this is a neighborhood around 4, which is our x value. We are asking what y value will be approached as we tighten this neighborhood. That's really what a limit is. So as this neighborhood gets smaller and smaller, what y value seems to be approached. In this specific case, notice how 1 is in this green area, and as this neighborhood gets tighter and tighter, 1 will be getting approached. In fact, infinitely close. This is very crucial to limits as we're considering what happens as we get infinitely close to certain numbers. So let's evaluate the following example. f of x is equal to x cubed is the graph shown right here. Evaluate the limit as x approaches 2 of x cubed. Look at the corresponding y values for all x's close to x equals 2. So let's take a pretty simple x actually. X, right, x equals 1, x equals 3, and let's look. So far, pretty big, nothing helpful. As we get closer and closer though, we notice that from the left side, which we denote as 2 from the negative side, f of x gets increasingly close, or actually infinitely close to f of x is equal to 8. So, as we approach 2 from the left side, 2 minus, remember, 2 superscript minus, not minus 2, not 2 minus like this, 2 superscript minus, f of x gets increasingly close to, f of x equal to 8. Also from the right side, which is 2 plus, as we get here, f of x gets increasingly close to, so f of x gets increasingly close to f of x equals 8. Therefore, we can conclude that as x gets infinitely close to x equals 2, but remember, very crucial part of the limit, never exactly x equals 2. We don't evaluate x equals 2. F of x gets infinitely close to y equals 8. Or, in other words, writing in limit notation, the limit as x approaches 2 of x cubed is equal to 8. To evaluate a limit, we don't have to look at its graph. Take the following limit. Limit as x approaches 5 of x squared over 3. Our first step should generally be to try some sort of substitution. So let's try that. The limit as x approaches 5 of x squared equals 3. Let's try substituting x equals 5 here. 5 squared over 3, 25 over 3, but this may seem a bit counterintuitive because we just said that the limit approach looks at values as they get closer and closer to a certain x, but never exactly at that x, in this case x equals 5. While that's true, in this case we can actually do that because the graph is known as a continuous graph, and we will define what a continuous graph is later on but for now you just need to know it kind of looks like where there's no holes and there's no gaps. So the limit is just the actual value. We notice this because we solved the limit with no trouble. If we get an undefined form or some indeterminate form, then we know that substituting doesn't work. So evaluate the limit as x approaches 2 of x squared minus 4 over x minus 2. So can we simply substitute, and is this limit equal to 2 squared minus 4 over 2 minus 2, which is 0 over 0? No. Now, you may be impulsed to just say, oh, the limit is undefined, or the limit does not exist, which do not say. Limits are never simply undefined. This is just not in their nature. Rather, we didn't optimize our solution. We can optimize this. We can make it better. You don't believe me? Let's take a look. Take x equals 2.01. If we let f of x equals the following, then f of 2.01 is 4.01. Now let's try f of 1.99. This is equal to 3.99. So the limit actually does seem to exist, and it appears to be 4. How do we prove that algebraically? Well, let's rethink. F of x is the following, which means that f of x is equal to, by factorization, x minus 2 times x plus 2 over x minus 2. And remember, in pre-calculus we learned we can do for any x that belongs to the domain of f, we can cancel out. Why? Well, because if x equals 2, then this does not work. We cannot cancel out because we're getting 0 over 0. So this only works if x belongs to the domain. But in that case, we get x plus 2. So f of x is equal to x plus 2 if and only if x is not equal to 2. Remember, in a limit, we ignore the exact value for the case where x is equal to x naught. Therefore, since this is true, we take values very close to x naught, but remember, never exactly at x naught. So we can use this new f of x to evaluate the limit. So the limit as x approaches 2 of x plus 2 is equal to 4 by substitution. And while again this may seem counterintuitive because now we're plugging in f of 2, and we just said that this only works if x does not belong to the domain of f, but this is after the step. But this is actually after the step, and this is totally acceptable in limits because we're just saying that as x does approach 2, we can plug in 2 and we'll get 4. And even if you take some super close value to 2, you're still going to get its super close value to 4. So whenever this happens, even if you establish this precedent, we can always, we can always substitute in limits once we've done the following. We can always cancel out in limits. This is just one of those rules. So here we saw sometimes we might need algebra or advanced theorems such as L'Hopital's rule to evaluate limits. So we only need to do very basic limits for now. So let's evaluate the following limits. I'll give you some time if you want to pause and try them out. Okay, let's start with number 1, yeah? So let's start off first by trying to substitute g of 5. Remember, we're going to define 3 of x minus 5 as g of x, and this as f of x for number 2. So if we try g of 5, we get this equal to 10. Since we don't have the 0 in our denominator, we don't have an undefined number, indeterminate form, or anything like that, we can simply say the limit as x approaches 5 of 3x minus 5 is equal to 10. Very easy, nothing to it. In general, especially when you have linear functions, we can prove this later on, but whenever you have linear functions, you can always just substitute to find the limit. So, try number 2. Now, unfortunately, substituting into f of 0 is not a suitable solution as it's undefined. However, by factoring, we get f of x is equal to x times x cubed minus 1 over x times x squared plus x plus 1. The x's can cancel out for us, and we will get that the x cubed minus 1 over x squared plus x plus 1 is going to be f or f of x, new f of x. Remember, x has to be part of the domain, but in limits, we don't actually take x equals 0. We take values very close to 0, infinitely close, but not 0, so we don't have to worry. And let's try substituting. This is a rule. So f of 0 is -1. So the limit as x approaches 0 of f of x is -1. Again, since we already simplified, we can always do this in limits since we're not taking exact values. We're only approaching, but getting infinitely close. Let's look at number 3, which is our graph. Evaluate the limit as x approaches -2 of h of x. Now, unfortunately, x of -2 is not actually defined. We have a hole in the graph. So we're going to have to look at the values around h of -2. So although h of -2 has a hole, we notice the values around it approaches about y equals 2.5 here. Notice here, as we get closer and closer and closer, like this, from the x, subtract x, the y's get closer and closer and closer to 2.5. And here, and here. So 2.5 seems to be our general consensus, that as x approaches 2, y approaches from both directions 2.5. So we can approximate the limit as x approaches -2 of h of x as 2.5. Again, even if there's a hole here, we can pretend like there is no hole since we don't care about its exact value, and we just figure out it's 2.5. Finally, for problem number 4, we get as x approaches -3 from the negative direction, which is in our chart. Remember, from the negative direction, x goes to -3 from the left. As x goes toward -3 from the left or from the negative direction or down, however you want to say it, the p of x is going to go to 2, let's say, approximately 2. We can't tell exactly from this chart, but we could say it's 2. And if we look at the other direction, as we go from -3 plus, so as x approaches -3 from the positive direction, we see that p of x also goes to about 2. So both of these will kind of close in on 2, so we can determine that the limit is about 2. So the limit as x approaches -3 of p of x is approximately 2. Hopefully this helped, and if you have any questions or concerns, feel free to reach out to me and I can answer. Remember, this is strictly for general computation, not for proofs. Proofs may be on a later video. However, we are simply trying to figure out intuitively what a limit is and how we can find it. Thanks for watching.